All right, let's dive in. Today, we're talking about something truly on the cutting edge of engineering, composite additive manufacturing. Or, to put it simply, how we're literally starting to 3D print the future of aerospace. This one sentence from our source material really just nails the whole story we're exploring today. It's this incredible tension, right? On one hand, you've got this absolutely game-changing technology, but on the other, you have these massive, massive hurdles that are keeping it from, well, completely taking over. It's a classic tale of revolution versus reality. And believe me, the stakes could not be higher. We're talking about a market for 3D printing aerospace parts that's set to explode to over $3.6 billion by 2032. So yeah, this is not just some niche experiment. This is a multi-billion-dollar shift in how we build the very things that fly. So let's get right to the core of it. Why is all this happening right now? Well, the aerospace industry is in this relentless, never-ending pursuit of aircraft that are lighter, stronger, and way more fuel efficient. And that demand, it's pushing traditional manufacturing to its absolute breaking point, forcing engineers to look for a completely new way to build. Okay, so take a look at this. It's the perfect before and after. Traditional methods, what we call subtractive manufacturing. It's kind of like sculpting. You start with a big, solid block of material and just carve away everything you don't need. I mean, think of all the waste. Additive manufacturing is the complete opposite. You build the part up, layer by tiny layer, using only the material that is absolutely necessary. This means way less waste, much faster production, and you can create shapes that were literally impossible before. And this is where we get to the real magic. It isn't just the printer itself. It's a whole new design philosophy called topology optimization. So instead of an engineer designing a part based on, their intuition, a super powerful algorithm figures out the most efficient way to place material to handle specific forces. We're shifting from a world driven by form to one driven by pure performance. And this slide just walks you through it beautifully. See? You start with a simple blocky shape. You tell the software, okay, these are the forces this thing needs to handle. Then the algorithm just carves away everything that isn't doing any real work, and what you're left with is this incredible, almost alien-looking structure. It honestly looks more like bone than a machine part. And the result of all this? Airbus used this exact process on a little cabin bracket for the A320, and they achieved a staggering 45% weight reduction. Now, I know, that might not sound like a lot for one tiny part, but multiply that across an entire aircraft, and you are saving tons of fuel and carbon emissions over its lifetime. It's huge. So we've kind of covered the why. Now let's get into the how. What are these amazing machines actually printing with? We're talking about some seriously advanced stuff here. You've got high-performance thermoplastics like PEEK, which are perfect for inside the cabin because they're flame retardant. Then there are thermosets for super precise parts. And then you get into the really extreme materials, metal and ceramic matrix composites. These are designed for the absolutely brutal environments inside a jet engine. They can withstand incredible heat and stress. But of course, you need different tools for different jobs, right? And this table shows there's no single best printer. You've got fused deposition modeling, or FDM, which is great for thermoplastics, but as we'll see, struggles with strength between its layers. Then there's selective laser melting, or SLM, which can create these incredibly precise metal parts, but man, is it expensive. And then you have the absolute giants like automated fiber placement, or AFP, which can build huge things like a whole fuselage, but the cost and complexity are just immense. Which brings us to the central question of this whole explainer. If this technology is so revolutionary, what's the holdup? Why can't we just print an entire airplane today? Well, it really boils down to these three massive challenges. First up is consistency. You have to be able to guarantee that the millionth part you print is just as perfect and just as strong as the very first one. Second, certification. Aviation is built on safety standards, and there's just no rule book yet for certifying these brand new types of parts. And third, cost and scale. A lot of these processes are still just too slow and too expensive for real mass production. Okay, let's zero in on that consistency problem, because it's rooted in this really key scientific concept, anisotropy. It's a fancy word, but it's actually a simple idea. Because these parts are built in layers, they have a grain, kind of like wood. They're super strong along the direction of the printed layers, but they're much, much weaker between those layers. And this chart, wow, it just drives the point home. The strength between the layers, what engineers call the Z direction, can be 30 to 50% weaker. than the strength along the printed plane. That is a massive problem when you're designing a critical part that has to take forces from all directions. It's really the technology's Achilles heel right now. And even if you solve all the technical problems, you slam right into the wall of certification. The existing rulebook was written for parts that were carved out of a solid block of metal. It has no way to account for things like how well the layers are bonded or the thermal stresses from a laser. Until brand new standards are written, these parts are going to stay in non-critical applications. But that is not where this story ends. Not at all. For every single one of these challenges, there's an army of brilliant engineers working on a breakthrough. So let's look at how they're solving these problems and literally designing the future of flight. So to fight that whole anisotropy problem, we have continuous fiber reinforcement. Instead of just printing with plastic, these incredible machines lay down unbroken strands of carbon fiber. It's like building superhighways of strength exactly where they need to go. This creates parts with a strength that's starting to rival traditionally made components. Next up, we're actually making parts intelligent. By embedding tiny sensors directly into the material while it's being printed, we can create structures that monitor their own health in real time. Just imagine a wing that can literally feel stress or detect microscopic damage before it ever becomes a problem. That's the amazing promise of self-sensing structures. And finally, the vision is becoming so much bigger than just performance. There's a huge push to make this technology truly sustainable. And this means developing new types of composite materials that can be fully recycled and designing printing processes that use far, far less energy. And this slide really gives you the full picture. The wins are huge, no doubt. Dramatically less waste during production and lighter planes that burn less fuel. But there's a real challenge here, and that's the high energy use of the printers themselves. True sustainability means we have to optimize this entire equation. This quote just sums up the ultimate goal perfectly. It's not enough anymore to just build better parts. The real mission is to create a fully circular system where the materials from an old aircraft can actually be used to print a new one. A cradle-to-cradle model where absolutely nothing is wasted. Which leaves us with this one final thought. We are witnessing a fundamental shift, moving away from assembling parts and towards printing entire systems. The challenges, yeah, they're immense, but the progress is just undeniable. So the question is no longer if this technology will transform aerospace, but how soon and how completely. I mean, will we one day look back at building planes with rivets and sheets of metal the same way we look back at steam engines? Only time's going to tell.